You ever stop and think about what's actually inside your phone that makes it work? Or your computer? It all boils down to this one tiny, incredible component invented decades ago that is literally the bedrock of all modern electronics. Today, we're pulling back the curtain on the Bipolar Junction Transistor, or the BJT. So where did it all begin? Well, it started right here with these three guys at Bell Labs. Back in 1947, they stumbled upon something they called the transistor effect. And it was such a massive deal that it snagged them a Nobel Prize and, no exaggeration, kicked off the entire digital revolution. This is more than a story about silicon. It's about the moment that completely reshaped our world. All right, so here's what we're going to cover. First, we'll get our heads around the BJT as a kind of electronic valve. Then, we'll dig into the three different personalities it can have. After that, we get to the really fun part, its magic amplification trick. And we'll wrap up by clearing up a super common point of confusion around the term saturation. So let's just jump right in with the big question, what on earth is a bipolar junction transistor? You know, the easiest way to think about it is with a really simple analogy. Picture a big water pipe with a valve on it. It takes just a little bit of effort to turn the handle, right? But that tiny twist controls a huge gush of water. Well, a BJT is exactly like that, but for electricity. A tiny little stream of current at the control input unleashes a massive flow through the main part. So how is this little marvel actually built? Well, check this out. It starts as a simple block of a semiconductor, usually silicon. Then, through this process called doping, we create three very specific layers inside it. You get a heavily doped N-type layer we call the emitter, a super thin and lightly doped P-type layer called the base, and then a moderately doped N-type layer called the collector. It's this NPN sandwich structure that's the secret to the whole thing. And each of these layers has a very specific job. The emitter's whole purpose is to emit, or just spew out a ton of electrons. That's why it's so heavily doped. The base, well, that's our control handle. The fact that it's so thin and lightly doped is what lets a tiny current have such a huge effect. And the collector? Its job is simple, to collect all those electrons that make the journey across. Nothing here is by accident, it's all precision engineering. Okay, so three terminals means, you guessed it, three currents. We've got the base current, or IB, the collector current, IC, and the emitter current, IE. And the best part is they follow this beautifully simple rule. The current going out through the emitter is just the sum of the two currents coming in. That's it. Keep that little equation in your back pocket. It's absolutely fundamental. All right, so now we get to the really interesting part. A BJT isn't just one thing. It's kind of like a chameleon. Depending on how you hook it up, what voltages you apply, it can act in three completely different ways. And that's its secret weapon. And here they are, its three main personalities. If you turn both of its internal junctions off, it goes into cutoff. Basically, it's just an open switch doing nothing. Now, if you turn the base emitter junction on, but keep the base collector junction off, you get forward active mode. This is where the magic happens. Amplification. And finally, if you turn both junctions on, it's in saturation, where it acts just like a fully closed switch. Let's look at cutoff mode first. As you can see happening here, when we set up the voltages to turn both of those internal junctions off, these barriers, we call them depletion regions, just grow and effectively create a wall. No electricity can get through. The base current, collector current, emitter current, they all flatline to zero. The valve is slammed shut. And now for the main event, forward active mode. Okay, watch this. We turn on that first junction, the base emitter one, and bam, a flood of electrons gets shot out of the emitter into that super thin base. But here's the trick. Because that base is so thin and barely doped, only a tiny, tiny little trickle of those electrons actually combine there and become base current. The vast majority, they just shoot right across and get sucked up by the collector. And that right there is the whole game. This incredible little phenomenon actually has a name. The source material puts it perfectly, saying, the fact that most of the electrons entering the emitter can exit the BJT through the collector is referred to as the transistor effect. And that one single effect is what makes this little component an absolute powerhouse. So, this transistor effect, what's it actually good for? Well, this leads us straight to the BJT's most famous party trick, amplification. It all boils down to one simple, just beautiful little formula. The collector current, IC, is equal to the base current, IB, multiplied by a number called beta. That's the forward current gain. This is the entire mathematical secret to how amplification works. So what kind of number are we talking about for this beta value? Well, for a very standard run-of-the-mill BJT, a typical value is right around 100. So a gain factor of 100. Okay, so let's connect the dots here. What this means is that for every one single electron's worth of current we feed into the base, we control a flow of 100 electrons through the collector. We're using a tiny little whisper to control a massive roar. That is amplification. And this is where it all comes together in the real world. You can take a weak signal, maybe from a microphone, and feed it in as that tiny base current. The BJT then creates a much, much larger version of that exact same signal as the collector current, a signal now strong enough to do real work, like drive a speaker. This is how we make the quiet loud. Okay, for our last section, we really need to tackle something that trips up pretty much everyone when they first learn electronics, and that is the very confusingly named saturation mode. Okay, here's the problem. The word saturation means one thing for our BJT and something completely different, almost the opposite really, for its more modern cousin, the MOSFET. For a BJT, saturation means both junctions are on, the faucet is wide open, and it's just a closed switch. The collector current is maxed out. But for a MOSFET, saturation is its main amplifying region. It's a huge source of confusion. And hey, if you're thinking, wow, that is confusing, you are not alone. As one expert puts it, this duplication of terms is a well-known headache in electronics, but we're kind of stuck with it, so it's just something you have to be aware of. So what's the big takeaway here? The absolute bottom line. If you are building an amplifier with a BJT, you have to keep it in that forward active region. That's where you get the control you need. The BJT's saturation region is for when you just want a simple on or off switch, not a smooth amplifier. All right, let's do a super quick rundown. A BJT is an electronic valve controlled by current. Its sweet spot for amplification is the forward active mode. The magic formula is IC equals beta times IB. And finally, when somebody says saturation for a BJT, you should immediately think fully on, closed switch. We've come an impossibly long way from that first clunky transistor at Bell Labs. Today, we don't just have one. We have trillions, literally trillions of them crammed onto a single computer chip, running basically our entire civilization. Which brings up one last question. In a world with that kind of mind-boggling complexity, does it still matter how one single solitary little switch works? I think it absolutely does, because at the heart of every complex system, you'll always find a few simple, elegant principles. Thanks for joining us.